My name is Nalin Pai. I'm a distinguished engineer in the CTO's office, and I lead the architectures around some of the use cases that we've spoken about. That's the network edge and the AI. Today, we will specifically look at a network slicing use case that we have enabled on top of the BlueField 3 DPU. And the area that this applies to is 5G and telco, but it kind of also leads into some of the edge inferencing that we kind of spoken about earlier. So I think this was a question that was asked earlier as to what do we exactly run on the BlueField 3, right? So this diagram kind of deep dives into that a bit more. So on the screen you see a BlueField 3. You have two blocks. The block at the bottom is a embedded switch that comes as a part of the BlueField 3. It's a completely hardware accelerated pipeline. The block on the top are a bunch of ARM cores that again reside on the BlueField 3 DPU, right? So what we have done in Arrcus is we have taken the Arrcus software, we run it in a container directly on top of the ARM cores. That way you don't have to kind of run Arrcus on top of your host CPU, and you can save those cycles for I guess the more interesting stuff. Now going down to the bottom block, as I said, it's an embedded switch. So we use the NVIDIA Doka APIs to create a routing pipeline, directly on top of the embedded switch. So as an example here, this is just a sample pipeline, but this pipeline is capable of taking packets coming in on the wire or from the host that's connected to the BlueField 3, and then doing your regular networking functions like bridging, tunnel termination, prefix forwarding, again maybe an encapsulation, and then forwarding it out wherever it needs to go, right? So this is pretty much a fully functioning router that resides on the BlueField 3 itself. All right, so this is the demo that I'll be showcasing today. We're going to shift focus a bit. This is more 5G telco centric. This was a use case that we addressed specifically for a telco customer. But what you see here is, at the top you see a standard 5G control plane with all these standard 5G components like the AMF, SMF, and the UPF. On the left-hand side, you see a couple of 5G endpoints. The red and the blue squares on the left-hand side are 5G endpoints. They're connected to a G Node B or a base station or a 5G base station, which in turn is connected to a BlueField 3 that's inserted into a standard server. Moving to the right-hand side, we see a MEC site, which is a mobile edge compute site, where again you have a server that's deployed there that's running MEC workloads. This could be, for example, an application that's doing AI inferencing at the edge. But then again, we have a BlueField 3 plugged into that server. And in the middle, you see a IPv6 network that's capable of transporting SRv6 packet. So we are using SRv6 as the underlay for this specific use case. And at the bottom, you see a data center, and the requirement really is to be able to connect all these pieces, right? So the RAN on the left-hand side, to the MEC site on the right-hand side, to the data center down below, all over an IPv6 network that's SRv6 capable. So you will see two things as a part of this demo. You will see network slicing in action using SRv6, and by that I mean the ability of SRv6 or to leverage SRv6 for tenant isolation as well as traffic engineering. So as a part of the demo, you will see two tenants. The red UE and the red workloads are in tenant 1, and the blue UE and the blue workload is in a different tenant. Finally, we will also showcase a complete IPsec offload between the MEC site and the data center using the BlueField 3's capabilities. But last but not the least, we have an Arrcus piece called as the MUP controller at the top. And what this really does is this is responsible for plugging into the 5G control plane, extracting information, and then distributing that over BGP using standard RFC extensions that we've helped develop for the SRv6 mobile user plane. And this information is then distributed from the MUP controller to the MUP gateway, which is the BlueField 3 on the left, and what we call as the MUP PE, which is the BlueField 3 on the right. So these BlueField 3s are actually acting like your traditional PE as you kind of as opposed to PE, and the provider and the Arrcus instances in the middle act as a provider routers. Yeah, does it play the video? Okay. So what you see here on a screen is a web browser running on the red 5G user endpoint. This browser is trying to reach out to the red workload that's deployed in the MEC site on the right hand side of the picture. So we'll kind of load the pages a few times. You will see that we settle down to around 200 milliseconds of average latency for loading the page. Let's kind of move over to the blue user endpoint, loading a page from the blue workload. You will see that the average load time is about 100 milliseconds. And what's really happening here is that the BlueField 3 that was functioning as the MUP gateway is steering traffic for the two tenants down two different paths through the SRv6 core, thereby kind of placing the latency sensitive traffic into the into the lower latency part of the network, and the higher latency and the traffic that's not so sensitive can flow down the regular path. So let's see what's happening under the hood. This is the MUP controller piece that we saw at the top. So this piece plugs into the 5G control plane, extracts relevant information, the user endpoint addresses, the data networks, the number of different tenants, and it then massages this information and then distributes that over BGP, which is what you see at the bottom, using SRv6 mobile user plane extensions that we have helped standardize. And this information is then collected and then advertised both to the MUP gateway and the MUP PE over BGP. So let's kind of move on to the MUP gateway piece. So this is a BlueField 3, as I mentioned. We're actually on the ARM cores of the BlueField 3. And we have an Arrcus Arrcus container running directly on the ARM cores. So let's kind of attach to the container and again inspect the BGP tables inside that container. You will see that the very same information that was advertised by the MUP controller is now available on the MUP gateway piece. And what this is trying to show you is the BGP tables at the top and the bottom tables. What we're trying to do is we take the information that we received from the MUP controller and then we extract relevant information from it to first program GTP tunnel termination entries. So the GTP traffic coming in from a base station, we strip off the GTP header and we place the traffic in an appropriate verb corresponding to that tenant. So we have two verbs or network instances, N61 and N62. And then inside each of the respective verbs, we also learn the ultimate data networks, which in this case is the MEC workload running on the right hand side. And what you will see is that we have policies in place to color the routes to reach the appropriate MEC workloads appropriately so that they can be steered down different paths through the SRv6 network. So we see two colors in use here, 100 and 200. So now let's take a look at what's really happening again one layer below that. Yeah. So if we again this is again the gateway piece, but if we now take a look at some of the SRv6 policies that we have configured, you will find that we have configured two policies and specifically two ISIS flex algos to be able to kind of steer traffic down two different paths through the network. Algorithm 128 and 129 are the two different algorithmic computations. And if we go down to the bottom, you will see that we have the policies in place so that if we have a next hop that needs to follow down the SRv6 set of 128.13.1, it takes the algorithm 128 and therefore goes down one path. The next hop that needs to kind of go down the 129.13.1 goes down a different path, right? So this is a way by which we can learn the MEC route, the MEC workload reachability, map it to a next hop, and therefore map it to two different paths through the SRv6 network to reach the other side. Okay. So now, yeah. So just kind of it's a video. So how much you can do. You just have to wait. Yeah. So now we'll kind of take a look at the IPsec encryption and decryption capabilities. You see two screens here. On the left-hand side, we're running an iPerf client in the MEX site on the host. On the right-hand side, we're running an iPerf server in the server that's belonging to the data center. And as I mentioned before, the MEX site is connected to the data center via a completely offload IPsec tunnel that's kind of offloaded down to the BlueField 3. So if we start the iPerf client, you will see that we have about 80 odd different streams completely accelerated, and we're able to kind of reach a total throughput of about 60 gig per second of completely accelerated IPsec offload without using any of the host CPU cycles to achieve this. So let's kind of stop here and let's look at some performance numbers. So this slide kind of talks about some of the throughput numbers that we achieve with respect to BlueField 3 and without using a BlueField 3. So we kind of measured both the SRv6 mobile user plane performance and the IPsec performance in isolation. The gray bar demonstrates the throughput that we achieve without using the BlueField 3 for accelerating any of the networking or the SRv6 functions. So we see straight away a 3x performance improvement. And I mean here I need to point out that the BlueField 3s that we have had a 100 gig transceiver. So theoretically we could not go over 100 gig even if we wanted to, right? So we are kind of almost achieving the 100 gig throughput for SRv6. On the right hand side we see the performance for IPsec, and this is where you get the biggest bang for buck, right? So we were only able to push about 7.2 gig using about 6 host cores when we didn't have the BlueField 3. But when we enable IPsec encryption and decryption using the BlueField 3, we kind of go up to about 70 gigs and without using any of the host CPU cycles for this. Yeah, this kind of just depicts what I just said, right? You kind of go from using about 6 cores of the host CPU for doing IPsec to 0 cores, and you achieve about 10 times the throughput by using BlueField 3s.